Great. Thank you so much for the invitation. I'm very happy to talk, and ideally in a few months we can all meet again, but for now I'll try to do my best through Zoom. The plan is I want to tell you a bit about tropical ideals, which is this proposal we have worked on for the last few years of how to come up with algebraic foundations for tropical geometry. So maybe let me get started. So I'm going to start by just telling you the way I want to think of tropical geometry for this talk. I'm going to have a very basic stuff, so very basic setup. So think of tropical geometry as a tool that allows you to take classical algebraic varieties. I mean, it's enough if we restrict to affine algebraic varieties, so subvarieties of the torus or subvarieties of projective space or a toric variety. And you do this machinery of tropical geometry and you turn it into a polyhedral complex that is embedded in R to the n. Okay, so some concrete polyhedral complex that you get from tropicalizing the variety. And of course, as we know, then we cannot try to attack classical problems by trying to understand their tropicalizations and trying to see what information that we care about is preserved under this tropicalization map. Okay. So just to set up some notation, I'm going to be talking about tropical algebra and tropical polynomials. So let me just remind you of the notation, that you know what the notation is that I'm going to be using. So I'm going to denote by R bar the tropical semiring, and that, as I said, is just the real numbers together with infinity. And I'm going to use the tropical operations, tropical addition, which I'm going to think of the minimum, but it doesn't really matter. So for the pictures I'm going to draw, it's going to be the minimum. And tropical multiplication is addition. As we know, the tropical semiring is a semi-field, meaning it's an algebraic structure that satisfies all the axioms of a field, except that there are no additive inverses. Okay, so infinity is going to be my additive identity, and 0 is going to be my multiplicative identity. And then I'll be talking about tropical polynomials, and I'm going to denote the set of all tropical polynomials by this R bar brackets the variables x1 up to xn. So this is just a collection of all polynomials having coefficients in the semi-ring R bar in the tropical numbers, and the operations that you do with these polynomials are tropical operations, coefficient-wise tropical operations. So the tropical addition and tropical multiplication. Now let's talk a bit more in depth. Let me remind you how you tropicalize a variety in this sense. So if let's say you have V, the variety defined by an ideal in a polynomial ring with coefficients in a field. So let's say J is the ideal that defines the variety V, and J has coefficients, is an ideal in the polynomial ring with coefficients in a field K. Let's say your field K is a valued field, so it comes with a non-Archimedean valuation onto the tropical numbers. Well, how do you tropicalize the variety V? Well, what you can do is you can tropicalize polynomials first. So whenever you have a polynomial f, capital F in your ideal, in J, then you can tropicalize it, and I'm going to denote by trop F, by simply substituting addition. Whenever you see an addition in your polynomial, you turn it into tropical addition. Whenever you see multiplication, you turn it into tropical multiplication. And you apply the valuation to the coefficients. So you don't take, the coefficients you substitute by the valuation, and that way you get a tropical polynomial, meaning a polynomial in the tropical semi-ring. Then, well, that's how you tropicalize one polynomial, but you can tropicalize the whole ideal J, by just taking, so I'm going to denote that by trop J, tropicalization of the classical ideal J. And this is going to be, well, the ideal in the polynomial semi-ring generated by the tropicalizations of all the polynomials that were in J. Okay. And I'm writing here ideal generated by those tropicalizations, but that's the generation part is really not so relevant. It's just because maybe your valuation is not surjective, for instance. So the collection of all tropicalizations of polynomials in your ideal might not be closed under multiplication by scalar, for instance, if you want to close by that in case your valuation is not surjective. But that's pretty much what you have to do with all you have to do if your field is infinite, at least. So imagine a tropicalization of the ideal is just the collection of tropicalizations of polynomials in your classical ideal in J. And then this is how you tropicalize the ideal, but how do you tropicalize the variety? Well, the variety is just, we want to think of it as the zero locus of this tropical ideal, the tropicalization of your ideal, and that is going to mean it's just a collection of points in R bar to the n in n-dimensional tropical space, affine tropical space, such that for every polynomial in your tropicalized ideal, trop J, then you have this condition that the minimum is attained twice. That whenever you plug that point in R bar to the n into any polynomial, then the different terms that appear, at least two of them attain the minimum. Okay, so I'm sure this is very familiar to most of you, all of you, but just to have a very concrete example in mind, I want to, well, let's assume we take an ideal, a linear ideal, very simple linear ideal in two variables, generated by 2x minus y plus 1. So a principal ideal in two variables generated by one linear form. And let's say that the field this ideal lives is complex numbers with the trivial valuation. So everything evaluates to 0 to the tropical multiplicative identity. The zero locus of this ideal is, of course, just the line y equals 2x plus 1. And if we apply this procedure to that line to see how we tropicalize the line, well, what we would do is we take all polynomials in the ideal. So that's what I have here on the bottom left, J. By the way, can you see my cursor or not? I'm not sure if, yes, okay, good. So I'm pointing at things, but yeah, you can see. So yeah, so the ideal is just consists of the generator 2x minus y plus 1 together with all the multiples of that polynomial. So x times that polynomial is here, y times that polynomial is here, but also, like, for example, this one is, I think, 2x minus y. So 2x times the generator minus y times the generator, so that, or plus y times the generator, so that the xy terms cancel. No, just x plus, well, yeah, one combination of these two gives you this one, the one that's 2x times the generator plus y times the generator. So 2x plus y times the generator gives you this one. And of course, you have all multiples, an infinite collection there. But I want to have it explicitly because, well, what is the tropicalization of your ideal? Basically, it's just applying this procedure of just ignoring the coefficients in this case, just substituting them by their valuation, turning all these polynomials into tropical polynomials, and then requiring that the minimum is attained twice for all of them. Okay, and because the ideal is principal, is generated, the classical ideal is principal, generated by one polynomial, then it's enough. That minimum attained twice condition is going to be, it's just enough to check it for the tropicalization of the generator, and then that implies it already for all the others. So what we get is the usual line that we have in two-dimensional tropical affine space. Okay. Please interrupt me at any point if there are questions or something is not completely clear. So now let me tell you something about algebraic foundations. So what is this algebraic foundations project in tropical geometry about? Well, one way of thinking about it is that tropical geometry has mostly focused so far on studying the varieties, these polyhedral complexes that you get by tropicalizing classical varieties. And then usually, if you see a tropical geometry argument for proving something about classical algebraic varieties, for instance, it's about understanding these polyhedral complexes, some information about these polyhedral complexes, or something like this. But usually there's very little. It's a lot about the geometry and not so much about the algebra. And then there was this very influential paper in 2013, 7-8 years ago, by Jeff and Noah Giansiracusa that kind of started this area of algebraic foundations in tropical geometry. And they basically told us, well, we can also look at algebraic information, and not only at the polyhedral complex, not only at the geometric objects, but you can also attach some algebraic objects to these tropical varieties. And the way they presented it was in terms of, I mean, because there is no subtraction in tropical numbers, then, well, so classically you have the geometric side is algebraic varieties, and the algebraic side is ideals, for instance, if you're thinking about affine algebraic varieties. But in the tropical semiring, ideals is not really the thing you want to look at least at first sight, because there is no subtraction. So encoding which polynomials vanish in a variety is not just, it's not enough to just encode which ones are equal to 0 or infinity. Or so the way they presented it is instead they said that the algebraic information we should care about is a congruence, so some kind of equivalence relation on the semiring of tropical polynomials that depends on the ideal you're tropicalizing, and it encodes basically the which functions are equal, which tropical functions are equal in the tropical variety and which ones are not. So that was their motivation, and I won't tell you more details about that, but they had some notion of bent relation that you could associate to a tropical variety, and this was some algebraic information that we are interested in. Later in a paper with Diane McLagan, we showed that actually this bent relation that they talked about in this paper, that is the algebraic information we care about, it was also equivalent to just recording this TropJ, as I described it below, the tropicalization of the ideal. So just take all the tropicalizations of all your polynomials in the ideal. That encodes the same information as the bent relation that Jeff and Noah had introduced before. And well, Jeff and Noah had seen already that this algebraic information encodes more than just the tropicalization of the variety. So if you have this tropicalization of the ideal, that's strictly more information than just knowing the tropical variety as a geometric object. And here we showed that actually that's the case even with multiplicities. So the algebraic information also remembers. It does not only remember the tropical variety, it remembers the tropical variety with multiplicities in the maximal cones, but it's more than that. You get much more information than just the tropical variety with multiplicities. So it's more information, but still it's still tropical information. So the tropicalization of all these polynomials. And then this is kind of the project that some of us have been working on, which is to develop algebraic foundations, to develop this algebraic side of tropical geometry. Maybe there's a question here. Is the tropicalization of a principal ideal generated by the tropicalization of the generator? That's an excellent question, Anna. No, and we can even see it. Maybe this is the right point to talk about it. Yes. So here in this example, that's already the case. The classical ideal we had is generated by one polynomial, 2x minus y plus 1, and here all these other polynomials are multiples of this one. But when you tropicalize, that stops being the case. So you still have this tropicalization of the generator, and second one and third one are still multiples of this top one. But here, because we had obtained this one as this, or 2 times this one minus that one, and you don't have subtraction in the tropical numbers, then using these two, using x times the generator and y times the generator, you cannot get rid of the xy term no matter what operations you do. So you will never be able to generate this x squared plus y squared plus x plus 1. And you need to add this one as a new generator, that's an extra generator for your ideal, and so on. And in fact, these tropical ideals are generally infinitely generated. It's not enough to just have finitely many generators. There's always some other polynomial that you will need to add that is not a multiple of the previous one. Yeah, so we'll talk more about that. I think that's part of the. But yeah, that's a great question. And then developing this algebraic side. Well, why are we interested in developing this algebraic side of tropical geometry? Well, we kind of want to mimic the notion of a scheme for an algebraic variety, for a tropical algebraic variety. And for instance, that would allow us to distinguish. If you have seen this example of here's a tropical variety that can be decomposed in 2 ways as a union of irreducible tropical varieties, meaning a balanced polyhedral fan that can be decomposed in 2 different ways as a union of irreducible, like minimal balanced polyhedral fans. You can decompose it as a line union quadric, or you can decompose it as a union of 3 lines. And geometrically, you cannot distinguish. I mean, the union of these 2 is the same as the union of these 3. But if you attach some algebraic information to your variety, and not only think of it as this geometric object, but maybe with some algebraic information, then well, you can decide if the algebraic information corresponds to line plus quadric, or to just 3 lines. So that's tropical schemes, of course, would be much more than that, but this is one concrete instance where you would want to have tropical schemes. Also, it would be very nice to have to be able to study these tropical varieties purely from the tropical side, purely using tropical machinery. Like if we could do some tropical algebra and we could study these tropical ideals, these tropicalizations of ideals, by just doing some tropical operations, that'd be nice, instead of always having to think that it's the tropicalization of something classical and then having to do some classical arguments. Maybe there's something to gain if we learn how to do things completely tropically. And well, I'm not sure if this is if the way we're proposing this is gonna include non-realizable tropical varieties, but in principle, you would want to maybe have some tropical machinery that allows you to deal with these non-realizable tropical varieties, meaning with polyhedral complexes that look like tropical varieties. They're balanced polyhedral complexes and satisfy the structural conditions that tropical varieties satisfy, but that are never the tropicalization of something classical. Maybe your machinery allows you to deal with these as well. So there's lots of things you might want to gain from developing algebraic foundations. And then, well, one possibility, maybe the first idea you would think about is, well, maybe doing algebraic tropical geometry is just thinking about this semiring of tropical polynomials and just thinking about ideals there. Let's consider maybe what we need to do is just understand the theory of all ideals in this, all possible ideals in this semiring of tropical polynomials. Maybe that's the way to go. But the thing is that ideals, or at least general ideals, there are not very nice. So, for instance, as we just discussed, this is not an Ethereum semiring in the sense that ideals there are infinitely generated. Even this simpler example, tropicalization of the ideal generated by x minus y, the classical ideal x minus y. Well, here you have a principal ideal, but when you tropicalize it, well, let's think about the tropicalization of this for a second. Tropicalization of the generator is x plus y. You forget about the coefficients, they have valuation 0, 1 and minus 1, so you get x plus y. But you also get x squared plus y squared, because in this classical ideal, you have x squared minus y squared, so that tropicalizes to x squared plus y squared. In the classical ideal, you have x cubed minus y cubed, so that tropicalizes to x cubed plus y cubed, and so on. So you have all in the tropical side, you get all the sums of the powers of the same degree of the variables. But the same thing that Anna was just asking, here, tropicalization of the classical ideal was principal, it was generated by just one polynomial, but here like these polynomials that I'm adding are not multiples of the previous. So x plus y, whatever you multiply it by, you can never get rid of the term in the middle, the xy term, because tropically there is no cancellation here. This is an idempotent semiring. So yeah, you just take the minimum of the coefficients, but the coefficients never disappear. You cannot cancel. There are no additive inverses. So yeah, x squared plus y squared is not a multiple of this one, and then x cubed plus y cubed is not a multiple of these two. It's not a combination of multiples of these two, and so on. So the ideal, already even for these ones that we care about tropicalizations of classical ideals. What we get might be infinitely generated. So that's one disadvantage of ideals in the tropical semiring. But maybe more seriously for us is that the varieties of general ideals in the tropical semiring can be very random, very arbitrary, but not so random, but can be much more general than what we think of as a tropical variety. So first of all, what do I mean by a variety of an ideal? Just the same definition we said before. So if you just take one tropical polynomial, the zero locus of that tropical polynomial, the hypersurface defined by that polynomial, is just the condition that the minimum is attained twice. And yeah, by the different monomials by the different terms in the ideal, in the polynomial. And then for an ideal, so a collection of polynomials, then the variety is just the intersection of all the varieties of the polynomials in the ideal. Just the same definition. You can do it. Before I told you that this was the definition for tropicalizations of classical ideals, but of course this makes sense for any ideal, even if it's not the tropicalization of a classical one. And the thing is that using this definition, which is what we think of the definition of variety of an ideal in the tropical semiring, these varieties can be they don't need to be a polyhedral complex, for instance. And this is very related to the issue, to the fact that ideals are infinitely generated. So because ideals are infinitely generated, then the variety of an ideal in principle is cut out by like infinitely many conditions, that the minimum being attained twice. And those infinitely many conditions, even though each of them is polyhedral, they can cut out a non-polyhedral set, like a curvy set that doesn't really look like a tropical variety. So maybe, yeah, this is one argument, that maybe all ideals is not the right class of things to consider for tropical geometry. We're considering too much. Victoria's asking, would we get the same issues if we identify things that have the same support as the tropical variety? That have the same support as a tropical variety. So yeah, I think what you're referring to here is that maybe so another way of doing this would be to identify polynomials that give rise to the same piecewise linear function. So don't think of polynomials as just collections of tropical monomials, but maybe think that two polynomials are the same if they define the same piecewise linear function, just as a function from R to the n into R, for instance. So you can definitely do that and try to develop an algebraic theory like that, but at least in my view, you would be losing the algebra by doing that. If you identify polynomials whenever they are the same geometrically, then that's kind of you're losing the scheme structure that you're trying to construct, and instead you're just looking more at the geometry. So maybe what I would say is that maybe this is a good notion for what radical ideals should be. So ideals that correspond to varieties, but that have the same information as just the geometry of the variety. But if you want to go beyond radical ideals and maybe have different structures, different scheme structures on the same variety, then maybe you don't want to identify things that are the same geometry. Not sure if that's what you meant, but okay. So that's, yeah, varieties can be fairly arbitrary, no polyhedral. So we would be leaving tropical geometry if we just consider all ideals here. And then one last thing that you might not like about all ideals is that the Nullstellensatz is not true in this polynomial semiring, in the tropical polynomial semiring, in the sense that there are proper ideals, for instance, the one generated by x plus 1 and x plus 2. There are proper ideals. This is a proper ideal of polynomial of the tropical semiring in one variable. So in this here, you don't never have a constant term, for instance. You can never get a constant term as a combination of these two, but still the variety is equal to the empty set. So the first polynomial is the mean attained twice condition is saying that x has to be equal to 1, and the second polynomial is saying that x has to be equal to 2. So the variety is empty, but the ideal is not the full polynomial.
Felipe, does this suggest that maybe the tropical numbers are not whatever it means to be algebraically closed?
Yeah, maybe this is one. I think it has to do with other things. So the tropical numbers, I would like to think that they are algebraically closed, like they satisfy the fundamental theorem of algebra, and they are the tropicalization. I mean, you can find roots, and they are large enough for all your needs, I think. But I'm going to claim that this is a problem of the ideals that we're considering, that maybe the class of ideals is too large, and maybe we should restrict to ideals that are more special, that look more like the ideals that we are interested in.
So you don't expect, if you had like some bigger semi-ring or semi-field, that this would not be an issue? You say it's really a different.
No, I don't think so. No, like this does not. This example, for instance, I don't think it goes away if you just add more coefficients. You also want your coefficients to be like linearly ordered and a group. So I think this is already like quite maximal in that sense.
Okay, great, thanks.
So yes, I was saying, well, the idea to try to solve some of these problems is, well, maybe this class is too large. Maybe we're just considering too many ideals, and we should restrict ourselves to a class of ideals that is more manageable. Class of ideals that look more like the tropicalization of the classical ones, which we know have nice varieties, that varieties equal to polyhedral complexes, and have a lot of nice properties. So this is the proposal, and this is what we proposed with Diane McLagan in a paper maybe a few years ago, like 2016. It came out in the archive, and it's based on this simple observation that if you have an ideal, a classical ideal J with coefficients in a field K, then whenever you fix a degree D, and you look at the truncation of your ideal, so just consider all the polynomials in your ideal that have degree at most D, then that's of course a linear subspace. So it's closed under addition and under multiplication by scalar. And it's a linear subspace of the space of all polynomials of degree at most D, which you can think of as, well, by fixing a basis, the basis of all monomials, you can think of as your field to the set of all monomials of degree less than or equal to D. Okay. So whenever you take a degree and you truncate your ideal at that degree, you get a linear subspace. And then this is what we want to try to mimic in the tropical set. So let me introduce some notation here. If you have a tropical polynomial now, then let's say coefficient cu times coefficient of x to the u is cu, then when I write these brackets sub a monomial, I just mean the coefficient of that monomial in the polynomial. Okay, so these bracket notations is just coefficient of this monomial in that polynomial. And then, well, the fact that these truncations are linear subspaces, what that implies is that if you take the tropicalization of a classical ideal, let's call it I, so I is the tropicalization of a classical ideal J, then whenever you take two polynomials, f and g, two tropical polynomials, f and g, that are in that tropicalization, they have to satisfy this monomial elimination axiom. So the monomial elimination is the following. Suppose that the two polynomials, f and g, are such that there is some monomial where they have the same coefficient. Okay, so you have two tropicalizations of polynomials in your classical ideal, and then maybe in some monomial that is common to both, they have exactly the same coefficient, and that coefficient is not infinity. So the monomial is actually there. It's not the additive identity. Then, well, this is the tropicalization for someone in the classical ideal. This one is also the tropicalization of one polynomial in the classical ideal. So you can take the two polynomials in the classical ideal, and you can do some combination of them to eliminate that monomial that they have in common. And then in that way, you will get, when you tropicalize that new polynomial that you get by eliminating the common monomial, you get a polynomial h in your tropical ideal, in your tropicalization, such that now the coefficient of the monomial they had in common has disappeared. So it's now infinity. That monomial doesn't appear anymore in this elimination. And in all the other monomials that appeared, the coefficient has to have increased. So you have to have some coefficient that is at least the minimum of the two coefficients that you saw. And that's because when you take a combination of two monomials and you tropicalize it, then the valuation can only increase from the minimum one. You cannot be lower than the minimum one. And actually, well, this is a technical thing I have to add here so that this statement is correct. What I'm going to say later is that you have to have an equality if, like, the coefficient of the monomial that you get has to be equal to the minimum if these two coefficients were different. So if the coefficient of f was different than the coefficient of g, then there cannot be cancellation. And when you tropicalize this combination of the two polynomials, you have to get exactly the same valuation as the minimum. Okay. So this is some combinatorial condition that polynomials in the tropicalization of the ideal have to satisfy. And I would like think of it as a monomial elimination axiom. So it basically tells you that if you have two polynomials in your tropicalization that have some monomial in common, then you should be able to find some elimination of that monomial, meaning some other polynomial in the ideal where that monomial doesn't appear, and the other coefficients are kind of controlled by the minimum of them. And our proposal was that, okay, maybe this is the axiom we should impose for what are the ideals that we care about. So we defined, just look at an ideal in the tropical semiring. We're going to call it a tropical ideal if it satisfies these eliminations. Okay, if it satisfies this combinatorial condition. And this is maybe the class of ideals, or at least a more manageable class of ideals, as I'll show you later, that we might care about in tropical geometry. So maybe if you know about tropical linear spaces and matrix, and if you like that, I'll tell you that an equivalent way of saying this monomial elimination axiom condition is that whenever you take your tropical ideal and you truncate it at degree d, so just consider all the polynomials in your ideal where the degree of the polynomial is at most d, then requiring that this satisfies the monomial elimination axiom is exactly the same thing as requiring that this is a tropical linear space in your space of all tropical polynomials of degree at most d. Okay, so in that sense, this condition is exactly the analog condition that we had up here of that classical ideal satisfied. Whenever you truncate them, you get a linear subspace. It's closed under addition and multiplication. Well, here tropically, whenever you truncate them, you want more than just being closed under addition and multiplication, because tropical modules can be very weird. But among tropical modules, the ones that we like to consider as linear spaces, linear subspaces, the tropical linear spaces, those are the ones we should require here. So every truncation should be a tropical linear space. And this is, if you know about this a bit, if you have heard about this before, you know that this is related to matroids and evaluated matroids. So a tropical linear space is just a different way of thinking about a evaluated matroid. But for instance, if you're only interested in polynomials under the trivial valuation, so where the coefficients are either 0 or infinity, then saying that I is a tropical ideal is just the same thing as saying that when you consider the polynomials of degree at most d that have minimal support, then those collections of polynomials are the circuits of a matrix. Okay, so they satisfy this circuit elimination axiom, which actually looks a lot like this elimination axiom here. So in some sense, tropical ideals are ideals that satisfy this matroidal condition, coming from the fact that we want them to be to behave like linear subspaces, but in tropical form. All right. So maybe let me give you some examples to make sure that this is the central definition to the talk what a tropical ideal is. So let's make sure that we understand this definition relatively well. For instance, let's consider this tropical ideal generated by just one tropical polynomial x plus y in two varieties. Is this a tropical ideal? Well, I guess you can imagine the answer. The answer is no, and that's because, well, in degree 1 you only have one polynomial x plus y and all the scalar multiples of it, so that's fine. That's a linear subspace. That's a tropical linear space. But in degree 2, you have x times the generator, so x squared plus xy, and you have y times the generator, xy plus y squared. But this monomial elimination axiom would tell you that because you have two polynomials in degree 2 and they share this common monomial xy, then there should be some polynomial also of degree 2 that doesn't use that common monomial and it only uses the other two monomials. So that would, the monomial elimination axiom would be forcing you to have x squared plus y squared in your ideal. But as we saw before, x squared plus y squared is not here. It's not a multiple of x plus y. Okay, so and this is the reason why ideals satisfying this monomial elimination axiom are usually infinitely generated, because no matter how many generators you add, always this elimination axiom is going to force you to have to add like new generators due to the fact that tropically things cannot cancel out, but still you want to have these eliminations between monomials and between polynomials. Of course, another example is well, the motivation for all this, which is tropicalizations of classical ideals. Whenever you have a classical ideal and you tropicalize it in the way we saw of just substituting coefficients by the valuation and operations by tropical operations, you get always a tropical ideal, an ideal satisfying this monomial elimination axiom. And just in analogy to matrix, I want to think of these, or tropical varieties, I want to think of these as realizable tropical ideals. The ones that actually come from a classical object by tropicalizing, you can think of them as the realizable ones. But it's more complicated than that in the sense that, of course, there's a lot of them, or we expect a lot of them to be, most of them to be non-realizable. Even though we so far know few examples of non-realizable tropical ideals. So ideals satisfying this monomial elimination axiom that are not the tropicalization of a classical one. But just in analogy to matroids, we expect most of them, most of tropical ideals to not be realized. And here's an example of one. This is maybe one of the first ideals, tropical ideals that we realized were not realized, that we discovered were not realizable. So maybe, yeah. So it's a simple ideal. It's an ideal in two variables, x and y. So of course, coefficients are tropical numbers. And it's generated by polynomials where the coefficients are always 0 or infinity, so very simple polynomials. So the generators are sums of monomials, but those monomials need to be k plus 2 monomials that live inside a standard triangle of size k. So let me tell you what that means. So first of all, actually I can draw here. Let me see. By standard triangle, I mean, well, what's the geometry here? I think of monomials as lattice points in the positive ortho. So for instance, 0, 0 is like the monomial 0 is the multiplicative identity in the tropical world. 1, 0 is the monomial x. 0, 1 is the monomial y. So I identify monomials with the exponent vectors, and that way I can think of monomials as lattice points in the positive ortho. And then a standard triangle. A standard triangle is just a triangle that is vertical, horizontal, and 45-degree line here. So this is a standard triangle. And then this ideal is generated by collections of k plus 2 monomials inside a standard triangle of size k. So for instance, I have some examples here below. 3 monomials inside a standard triangle of size 1, those classified as generators. So for instance, these 3 monomials, 0, x, and y, they live inside a standard triangle of size 1. So this will be one generator of your ideal. This is the picture for 0 plus x plus y. This would be in your ideal. When I use 0, remember 0 is not really the additive identity, it's the multiplicative identity. So this term does matter here, 0. Here is another one. Here are 3 monomials inside a triangle of size 1. So this would be another polynomial that is in your ideal, y plus xy plus y squared. Here are 4 of them that live inside a triangle of size 2. So the sum of these 4 monomials would be another generator of your ideal. Here's 5 of them inside a triangle of size 3, and so on. So you can imagine, yeah, you can imagine this is going to be an infinitely generated ideal where the generators are these special configurations of points in the lattice, in the lattice monomial. And maybe I can tell you why this is non-realizable. So, well, first of all, it's not clear at all that this is a tropical ideal. Maybe it's clear that it's an ideal in the sense that it's closed under multiplication and by external polynomials, and that's because we see it here. It's closed under multiplication by variables. You take one of these generators and you multiply it by y, then all you're doing is like shifting the triangle upwards, and then it's still going to satisfy this condition of k plus 2 monomials inside a triangle size k. So it's closed under multiplication by monomials, and it's closed under addition basically because I defined it to be the ideal generated by these ones. So it's an ideal, but it's not clear that it satisfies the monomial elimination axiom. It does. So these are actually, yeah, these are, I'm describing the circuits of a certain matrix. These pictures that I'm drawing correspond to circuits of a certain matrix, and those circuits satisfy the monomial elimination axiom, the circuit elimination axiom. So they do satisfy the monomial elimination axiom. You do get a tropical ideal in this way, but it is not realizable. Why is it not realizable? Why can it not be the tropicalization of some classical ideal? We can see that already in this picture up to degree 3. Suppose it was the tropicalization of a classical one, of a classical ideal, then because you have 0 plus x plus y in your tropical ideal, then well, this has to be the tropicalization of something in the classical one. So some constant term plus some x term, linear term, something times x plus something times y. And you can first of all scale polynomial so that the constant term is a 1. And second of all, you can scale the variables, so maybe change x by 5 times x or by some scalar of x, so that all these coefficients are also 1. So what I'm trying to say is that without loss of generality, we would have 1 plus x plus y in J. So I'm assuming, yeah. So I'm assuming that the tropicalization of J is I. J is a classical ideal with coefficients in some field that tropicalizes to this tropical ideal. Then without loss of generality, J would have to contain some polynomial like this, 1 plus x plus y. But then, because J is an ideal, then you can take 1 plus x plus y and multiply it by anything, and you still get something your ideal. But classically, of course, you can create a lot of cancellations. So if you multiply it by, I think what I want to do is x squared plus y squared plus 1, and then minus x minus y minus xy. So this is some kind of carefully chosen quadratic polynomial so that there's a lot of cancellation when you expand this out. And then what you get after expanding all this is 1 plus x cubed plus y cubed minus 3xy xy. So this would have to be also in your ideal J. But then that means that the tropicalization of this polynomial would have to be in I, in your tropical ideal. And if you look at what the tropicalization of this polynomial is, it involves the constant. So it involves this monomial, 1 x cubed, y cubed, and xy. You forget about the coefficient. And then you would end up with 4 monomials that are 2 spread out, that do not live inside a triangle of size 2. They live inside a triangle of size 3. So in the tropical ideal, this is not one of our polynomials. But if it was the tropicalization of a classical ideal, then it would be forced to be there. Okay. So this is the kind of issues, the kind of things that can happen. And then in some sense, the degree 1 part of this ideal and the degree 3 part, or maybe let me say it like the realization space of the degree 1 part, like and the realization space of the degree 3 part are incompatible. You cannot find an ideal that tropicalizes in degree 1 to the right thing and in degree 3 to the right thing. They have to be. So yeah, so that's why this is not a realizable tropical ideal. Okay. Questions so far? Great. So now what I want to do for the rest of the talk is to convince you that this can be a useful notion for tropical geometry, for developing these algebraic foundations of tropical geometry. And I'm going to give you some results, some of the theory that we have learned about tropical ideals and how far we have advanced in understanding the algebra and also the connections between the algebra and the geometry for this class of tropical ideals that are not necessarily realizable, that do not necessarily come from a classical ideal. And basically, maybe the one way of thinking about it is that tropical geometry, the tropical semiring, the tropical numbers do not have additive inverses, but this monomial elimination axiom is kind of a substitute for that, and it's kind of even though you cannot subtract directly tropical numbers, we are requiring this elimination axiom that allows you to cancel out monomials that appear in different polynomials. So, well, the first thing you can do that is kind of immediate from the definition or follows directly from the definition is that there is a good notion of Hilbert function for tropical ideals. So let's say if you take a homogeneous tropical ideal I, one tropical ideal satisfying this monomial elimination axiom, then you can define the Hilbert function to be just the function that measures for every degree the codimension of. Remember, tropical ideals are those that when you restrict to some degree, when you truncate at some degree, you get a tropical linear space. And tropical linear spaces have a very well-defined notion of dimension. They are matroids. Matroids are all about having a good notion of dimension. So you can define the Hilbert function of the ideal to just measure what these dimensions are, or codimensions are of the different truncations of your ideal to different degrees. So, yeah. So this this is one way you could define it if you think about it in terms of tropical linear spaces. If you want to think about it more combinatorially, more in terms of matrix theory, this codimension is just measuring the largest size of a collection of monomials that you can pick, so that you never include all the monomials that appear in one of your polynomials in your ideal. So the size of a maximal collection of monomials that does not contain the support of any polynomial appearing in your ideal. That's one way of thinking about this codimension. And this is the notion of a basis in matrix, if you know what it is. This agrees with the notion you have of Hilbert function for classical ideals, in the sense that if your tropical ideal is a tropicalization of a classical one, which is not always the case as we saw, but in the case for the realizable ones, this notion of Hilbert function is equal to the Hilbert function of the classical one, meaning it measures the dimension of these different graded pieces of the quotient of the polynomial ring by your ideal. And then one of the first things we proved is that this was also in this paper in 2016, I think, that even for non-realizable tropical ideals, this notion of Hilbert function always agrees with a polynomial for large enough d. Okay, just like classical ideals, tropical ideals with this notion of Hilbert function, this Hilbert function eventually becomes a polynomial, and that means that tropical ideals have a notion of Hilbert polynomial. This polynomial that the Hilbert function eventually agrees with, that we can think about the Hilbert polynomial of the tropical ideal. Also remember, there was this problem of the non-Noetherianity of the tropical semiring, that you could have infinitely generated ideals, and therefore, yeah. So, well, that we cannot do anything about, because already the realizable ones are infinitely generated, they are not finitely generated. But if we restrict to this class of tropical ideals, we just consider the class of ideals satisfying the monomial elimination axiom, then we recover the Noetherianity condition in this sense, in the sense that you cannot find infinite ascending chains of tropical ideals. Okay, so there's definitely infinite ascending chains of ideals that are not required to satisfy the monomial elimination axiom. But once you restrict to just the ones that satisfy the monomial elimination axiom to the tropical ideals, then all the infinite ascending chains disappear, and every ascending chain has to be finite. So that's very good news if you want to do some geometry, because maybe there's a hope of having some notion of dimension, or just from the purely algebraic side. How do we prove these things? So far, one of the main tools we have for proving these kind of statements is the notion of initial ideals, which I'm sure most of you are familiar with. Maybe you know it in the context of classical ideals, but you can do the same for tropical ideals. So if you fix a tropical ideal, some of monomials, each with a tropical coefficient here, Cu, and you fix a weight vector W. So think of this weight vector as assigning a weight to each of the variables. Then you can define the initial term of the polynomial to be just, you collect all the monomials where the minimum is attained when you plug that W into the polynomial. So collect is another polynomial, tropical polynomial, where you collect all the monomials where this value coefficient plus W times U is minimum. So you collect the terms, the monomials where the minimum is attained at the polynomial. That's for one polynomial, but you can do it for the whole ideal. So now you have an ideal in a tropical ideal, for instance. Then the initial ideal is just the ideal that is generated by all the initial terms or the initial forms of polynomials in your ideal. So you do this also for classical ideals, and it's a very useful notion in tropical geometry. And the key fact is that this construction here preserves the matroidality condition. So if you start with a tropical ideal, you start with something that satisfies this monomial elimination axiom, then after taking all these initial forms, that is also going to satisfy the monomial elimination axiom. And actually, it preserves the Hilbert function. So you do not change the dimensions of these truncations. You do change the ideal, but the dimension in every degree stays the same. So So this is a very useful tool whenever you want to prove something for a tropical ideal. What you can do is maybe degenerate it using this weight vector. So take its initial ideal, find some think of it as a Grobner degeneration of the ideal, and then you get a simpler ideal because these initial forms are simpler than the full polynomial, and then maybe it's easier to prove it for the initial ideals.
I have a question about the geometry of this. So the initial ideals also have, at least in the algebraic sense, have an interpretation as some sort of some intersection with torus orbits in a toric degeneration. And
yes.
Is something like this true here as well in that on the topic?
It should be true. We have thought about this, and I don't think we have written it down, and we tried to make like a concrete statement, and I think in the end we didn't manage to do it. But I mean, we believe it's true that it should be a degeneration. Maybe you take your ideal is encoding some tropical variety, and then you degenerate it, meaning you go to some part at infinity, or you forget about the coefficients, and then that is what the initial ideal is encoding. Yes, that should be true. I think we haven't completely fleshed out the details on all of that, but that's something like that should be true.
Okay, great, thanks.
So now that we're talking about initial ideals, there's also this notion of Grobner complex for tropical ideals, meaning you do the same. You think of the partition of R to the n, the space of weight vectors. You think of the partition into different cells depending on what the initial ideal for that weight vector is. So you glue together different weight vectors if they give you the same initial ideal. That's what the Grobner complex is. And we prove that for tropical ideals, even though they might not be realizable, they are finite polyhedral complexes. The Grobner complex is always finite polyhedral complex. Okay, so the finite part is the important part here. It's a finite polyhedral complex. So Diane is saying, if the question is, are the initial ideals what you see at the boundary in a compactification, then I agree. It's essentially this. Yeah, okay.
I think that was the question. Thanks, Dan.
Yes, so we also have a notion of Grobner complex. This Grobner complex you can think of as a generalization of Grobner complex for classical ideals, because again, if your ideal is the tropicalization of a classical one, then the Grobner complex of the classical ideal and the tropical ideal are the same Grobner complex under this definition. But this notion makes sense even for non-realizable tropical ideals. So it's a bit more general. And then the variety of a tropical ideal, well, it's going to be a subcomplex of the Grobner complex, because, well, this minimum attained twice condition, that the minimum has to be attained twice, you can think of it as saying that the initial ideal contains no monomials. You never get one single monomial as the initial term of a polynomial. And then, well, once you know that the Grobner complex is a finite polyhedral complex, then you get as a consequence that the variety of any tropical ideal is a finite polyhedral complex. And remember, this was one of the things that we really didn't like about the class of all ideals in the tropical world. They were too general because the varieties could be non-polyhedral. Well, if we restrict to this special class of the matroidal ones, the tropical ones, the tropical ideals, then we recover this property that we like, that we feel we're doing tropical geometry if we're dealing with finite polyhedral complexes. And you can be more specific about how to attain this. So for instance, you can prove that there's a finite subset of polynomials f1 up to fk in your ideal that cut out the variety. Okay, so the set of points, minimum attained twice condition is enough to check it for these finitely many polynomials. Even though the ideal might be infinitely generated, the geometry is, as a set at least, is described only by these finitely many polynomials. Okay, so this is what you call a tropical basis in classical, for classical ideals, but I guess like this, it also makes sense for tropical ideals. And then maybe one more thing we can also prove is that you recover at least the weakness genesis, you restrict yourself to this special class of ideals, tropical ideals, in the sense that the only tropical ideal that has empty variety is the full polynomial ring. We also get rid of this example where we had proper ideals that have empty variety. Whenever you have that, it's because your ideal is not tropical. It doesn't satisfy this monomial elimination axiom. But among the tropical ones, among the matroidal ones, there's only one with empty variety, and that's the full polynomial semiring. So this is a non-trivial statement, and it's mostly hidden it's mostly a consequence of what Grigoriev and Podolsky do in this very nice paper about Null-Stellensatz for tropical polynomials. But we can express it like that for tropic, like this for tropical.
Felipe,
yeah.
question, actually.
Yes, of course, yeah.
Is K related to the Hilbert function? The K is in the slide before.
Yes, Anna. Sorry, didn't see the K. Yeah, that's a good question. I haven't thought much about how many polynomials you would need to cut out the variety. Of course, it has to be at least the codimension of your variety, but yeah, I'm not sure. For example, I don't know what a complete intersection would be, or how to tell if something is a complete intersection or not, just from the ideal. That's definitely a good question. Matt is asking, is the analog of the strong Null-Stellensatz for tropical ideals false or just not known? This is a very good question, Matt. We have thought about this for a while. It is not known in full generality yet. I think we know how to prove it for maybe 2 variables and 3 variables with constant coefficients, something like this. And we have some ideas for how to extend it, but it's been more complicated than what we thought. So far, the status is not known. And Diane is saying there is a bad bound on the size of a tropical basis in terms of the Hilbert polynomial for suitably saturated ideals. Okay, good. Anna, so you can ask Diane if you want to know more about that, using things like the Gotsman number. Okay, perfect. Okay, let me try to wrap it up. This is all that I've told you so far is work that we did in this first paper on tropical ideals, where we introduced this notion, but we have developed a bit more, we have studied a bit more the connections between the algebra and the geometry. So for instance, the fact that you have a Hilbert polynomial allows you to define notions like dimension or degree of a tropical ideal. Dimension is just the degree of the Hilbert polynomial, and degree is it's related to the leading coefficient of the Hilbert polynomial. And in a more recent paper that we published maybe 6 months ago or something in the archive, we show that these 2 notions, the geometric notion of dimension and the algebraic notion of dimension, agree in the sense that the variety of a tropical ideal is a polyhedral complex, and that polyhedral complex has dimension equal to the degree of the Hilbert polynomial, the algebraic dimension of the ideal. Okay, so these 2 notions agree. That's something. Yeah.
You say nice dimension because it could happen that there are, I mean, that there are sort of maximal components of small dimension as long as there's one maximum.
Exactly.
That is.
Yeah, just like tropicalizing a classical variety, it could have components, maximal components of different dimension. If it's not irreducible, then that can appear here, and I have a comment about that here later. But something else we prove in this paper is that it satisfies the balancing condition. So these polyhedral complexes that we get as varieties of tropical ideals do look a lot like tropical varieties, in the sense that the maximal cells have a multiplicity that you can tell just from the combinatorics of the tropical ideal, and these multiplicities make the polyhedral complexes balanced. So they satisfy the 0 tension condition around every cell of codimension 1. Okay? They cannot, all the cells cannot be just looking on one side, towards one side of the plane. They have to be spread out and satisfy the balancing condition. But yeah, as Martin was saying, there is this, we still have as an open problem to find what irreducible, find a good notion or a good property, at least that implies that the variety is kind of pure, for example, or that something you want to think as saying that the ideal is a prime ideal, or that the variety is an irreducible variety. There have been some, like, there's different ways you could try to approach this, but so far all of the ones we have tried, people have tried, they don't really capture all the things we want to capture about being prime or being irreducible. So they're either too restrictive or too general. I don't think there's a satisfactory answer to what prime or reducible is in the algebraic side. And then I'll just conclude with some questions that we have about this. Is every balanced polyhedral complex the variety of a tropical ideal? Yeah, so for even these non-realizable polyhedral complexes that are balanced, can they be the variety of a tropical ideal? At the beginning, we thought that maybe the answer was yes, but in a paper that we posted in the archive 2 years ago with Jan Dreisma, we showed that actually even Bergman fans of matrix, so these combinatorial polyhedral fans that are, you can think of as tropical varieties of degree 1, but there are some non-realizable ones, like the Bergman fan of this Bamush matrix plus the uniform matrix of rank 2 on 3 elements, if you know what that is. This one you can never attain as the variety of a tropical ideal. Okay, and it boils down to some old theorem in matrix theory of Las Verñas in the 70s that basically proves that there is no tensor product for matrix. Okay, so it has to do, there's a lot of combinatorics that is encoded by these varieties and by these ideals, and that this is not, that the fan of this matrix is not a variety of a tropical ideal, boils down to the non-existence of tensor products of matrix. We still don't know of a tropical ideal whose variety is a tropical variety that is not realizable. Okay, so all the examples we know a lot of non-realizable, or we know some non-realizable ideals, but all of them have realizable varieties. We still don't know ones that have non-realizable varieties. Other things we would like to do with this is to develop more commutative algebra for tropical ideals, like what's the sum, what's the intersection. The naive definitions don't work. This class of tropical ideals is not close to their sum, on their intersection. What are prime ideals? What should be the primary decomposition of a tropical ideal? What should be a free resolution of a tropical ideal? All these things we don't really know. And finally, how can you describe tropical ideals in a finite way? For instance, I described it to you as a sequence of tropical linear spaces that all the different truncations, but this is kind of infinitely much information. So how, maybe is there a way that if I just tell you the first 10 truncations and then I tell you and then continue like that canonically or generically or something, what does that make sense? How do we make sense of some concept like that? We don't know yet. So yeah, these are some of the questions that we have, and yeah, I think I'll end with that.